Hi, thanks, Richard. Again, my name is Kristen, and I'm with the Nature Conservancy, and I'm happy to present some work we're doing in the northern Sierra Nevada to look at links between forest and meadow restoration primarily on U.S. Forest Service lands and the water quantity benefits that can come from those restoration projects. So this work is being done by a large group of people, and at the Nature Conservancy it includes David Edelson, Mark Zimring, Ed Smith, Paul, and then we also hired Ecosystem Economics to do a benefit cost analysis, and that included both Bruce Aylward and Sarah Cruz. So this work is preliminary right now, but we're happy to share the results with you and hopefully get some feedback. So at the presentation, we had some really good comments last Friday. I'm going to go ahead to the next slide. The purpose of the study we're working on is, again, to evaluate whether forest and meadow restoration on a big scale on U.S. Forest Service land would provide water quantity and water timing benefits. So the idea is thinking into the future and taking a planning perspective to increasing the pace and scale of restoration on public lands. And we wanted to do two things. The first was an economic valuation to determine whether the water benefits could actually help pay for the activities. So forest restoration, what we're talking about is primarily forest fuels reduction through thinning or prescribed fire. And those activities cost money, so can the actual water benefits help to offset the cost of that work? And with climate change mitigation, the second point, we're trying to look at whether changes in the future with climate, so changes in the annual stream flow or the summer flow, can be mitigated by these restoration actions. So with the case of forest restoration, if you thin the forest and increase the water yield or increase the surface runoff, whether that could actually match some of the projected declines in stream flow in the future. So to do this, we first summarized what were we talking about in terms of forest fuels reduction and meadow restoration. So what were the benefits that came from these activities, including water, and where were we talking about doing these activities, like how much acreage are we actually needing to treat for forests to reduce the risk of high-intensity wildfire, and how many acres are actually in need of restoration across the northern Sierra Nevada. The reason we chose the northern Sierra Nevada from the McCollum watershed in the south on the map there up to the foothills, including the Truckee and the Carson flowing to the east, is that there's a lot of Forest Service land in this area. You can see the green color map that's showing you what is Forest Service land, and it's about 50% of these watershed areas. And the watersheds here on the map are clipped at the downstream end to either the large reservoir. So you can see the Feather River is a big watershed in the northern part of the map, and the reservoir at the bottom there is Lake Orville. If there was no large reservoir, then we clipped it to the stream gauge that was similar in elevation to those large reservoirs. So that was to be able to calibrate the climate change models. So we estimated how many acres we'd have to do of forest fuels reduction and meadow restoration. And then we could do both a benefit cost analysis, that's the economic component, and then the climate change mitigation. So first I'm going to talk about what are the water quantity benefits from forest thinning and meadow restoration. So forest thinning, the idea here is that if you remove some of the small trees, you can reduce the risk of what are being called mega fires or tropic fires, these large areas of high intensity fire. You're removing trees to reduce the fire risk, also potentially increase the amount of runoff. The way that I like to think about it is, in the past, the forest probably had gaps in it with large trees spaced out and some clumps of dense pockets of trees. But the forest, in essence, was using less water, and what I mean by that is the trees were transpiring less water in that sort of historical forest condition. And then today, the forest is considered overly dense with small trees, and that's a result of fire suppression, so fighting fires, and also sort of logging and taking out the big trees. And those practices have led to this forest condition where when a wildfire starts, it's got so much material, so much small, dense forest material to burn through that it can burn really big. And so forest thinning is a first step to, you can really reduce that risk around urban areas and also allow fire to move through thinned areas. So fire is a dynamic process, and we don't want to discourage all fire. That's not the idea here, but rather to make it so that when the fires burn, they're burning at a range of low and moderate severity with small pockets of that high severity fire versus a big high severity fire. So this is just summarizing, this table here is just summarizing studies on forest thinning and water yield. And actually they're more like clear-cut and water yield. So you can see here there's paired watersheds. So Bosch and Hewlett reviewed 94 paired watershed studies. What that means is there's two watersheds of similar size in similar elevation and climate conditions and forest type. And one watershed is treated, so either forest harvest for timber harvest, or thinned in the sense that we're talking about now with ecological thinning, a la GTR, the General Technical Report 220 and 237, which are guiding forest management here in California. And so when you look at these studies, either Bosch and Hewlett with their 94 paired watersheds, or Sahin and Hall reviewed 145 paired watershed studies, what they find is there's a water yield increase when you do this work. And so we adopted a range of 0.14 to 0.41 acre-feet of water increase per acre of restoration. And that's just representing a range of what's potential. And that's for 20 to 31% of basal area reduction, or basically it's equivalent to the ecological forest restoration level there. So you can see we took the amount from 100% and then calculated a range for what we would consider ecological thinning. We assume the water yield increase would occur in the wintertime, and we define the winter as from December to May. So we split the year into winter and summer. And a big assumption that we have is that these paired watershed studies at a small scale would scale up to the big Feather River scale. So this is a big assumption, and one that really has only been modeled in some other studies, and there's no real good on-the-ground empirical evidence yet that these large-scale projects would lead to this increase in water yield. So there's this gap in needing to understand, if we scale up, what is that going to mean for water yield. I'll also mention that of all these paired watershed studies, none of them are in California, are in the Sierra Nevada. So this is another major gap in the research, and one that's being addressed by Carolyn Hunsaker down at Kings River Experimental Watershed. And she's the furthest along with her research and is getting post-thinning water yield results. Also, Terry Hogue from Colorado School of Mines is researching water yield and forest thinning at Sagehen, which is an experimental forest outside of the Truckee area in the Truckee watershed. And then Roger Bales and the rest of his group, including Martha Conklin, are also researching this topic. So plenty of research going on and interest in determining the relationships between forest thinning and water yield. So I'm going to quickly go through meadow restoration, given that the focus was on forest thinning and water yield for this conference. I skimmed through this really quickly, but I'm going to touch on it now because I have a little bit more time. Meadow restoration, the idea here is that meadows are really important habitat areas for many different species, willow flycatcher, different species of amphibians, including the mountain yellow-legged frog and Sierra Nevada yellow-legged frog and Yosemite toad. And many of these habitats are degraded, the meadows are degraded because of many different reasons. But essentially, the storage in the meadow, so meadows can be thought of as a sponge is often the analogy that's made. And when a meadow is degraded, it no longer functions like a sponge. And what I mean by that is in the wintertime, in a degraded meadow condition, in the winter, the runoff from snow melt and precipitation just kind of flushes through the meadow and does not recharge the groundwater. And in a healthy meadow condition, those winter flows would not just sort of flow through the meadow in the channel, but would actually recharge the groundwater and go over the bank into the floodplain and really fill up the sponge that is the meadow. And the importance there is that at the end of the summer, that recharged groundwater in the healthy meadow condition is then feeding back into the stream and providing late summer base flow. So at a time when the flows would be really low in the stream, the meadow is actually providing cold water, which is important for those species in the meadow and downstream, and also could have some value for people because that's when our demand is high and we need water for electricity to power our air conditioners and other things, and we need water for water supply. So we searched the literature for pond and plug, also sometimes called plug and pond restoration, and this is a technique used to restore meadows to try and evaluate what the shift in the water amount would be. And there's only 2 studies that really quantify that change in the amount of water. There's one other one, Chris Hammersmark's dissertation, but he was not able to account for all the groundwater flow paths, so we just rely on 2 studies here to estimate 0.5 to 0.7 acre feet per acre shift in the water from the winter to the summer. So we don't calculate kind of flood attenuation benefits of meadows or any of the other myriad benefits from meadows, but we really focus on that shift in the timing of the water amount. So back to forest thinning here. This is just showing you an estimate of the past 10 years of forest thinning and prescribed fire work in the northern Sierra Nevada, and we use the U.S. Forest Service FACTS database to get this map made, and we estimate that about 46,000 acres per year is being managed for forest field reduction right now, and that represents about 0.2 to 12% of the watershed areas in each of these watersheds. So there's not a lot of, there is good work being done, but there's just not a lot of it being done at a big scale. So we estimate, this is now showing you what we would estimate that is needed to be done or what is potentially operable for forest thinning and prescribed fire. And to do this, we mostly use GIS to define what operable areas would be. So we excluded wilderness areas, wild and scenic, and roadless areas, which are, generally speaking, at the highest elevations in these watersheds. We eliminated slopes that are greater than 40 degrees, and anything that's further away than about 300 meters of a road, because those areas, you just, if there's not a road, you can't get the equipment to do the work. It's too steep, it becomes prohibitively expensive. So this is just a ballpark of what's actually operable for forest field reduction work. We also highlighted areas above 1,000 meters of elevation because that's what we consider kind of the lower end snow line, and we know that this relationship with forest thinning and water yield is going to be more dramatic in snow areas versus rain areas. So we eliminated some of the low elevation areas. And we estimate that about 182,000 acres per year is actually operable in the northern Sierra Nevada area. So quite a larger area, and it represents basically a threefold increase, 3 times increase from the 10 years pace and scale. And the biggest amount of the watershed would be 33% for the Feather River, so that's got the greatest operable area for the total watershed area. Most of the other watersheds like the Yuba, McCallamy, American, and Truckee are around 20%. For meadows, we used the UC Davis Meadows database that recently came out and showed you where the public meadows are. We focused on the green, the public meadows, and we eliminated meadows that have been typed, hydromorphic typed as dry or subsurface, because those types wouldn't be suited for pond and plug restoration. So we just isolated ones that we thought would be good for restoration. And then we assumed that 60% of the meadows were degraded. And that comes from an estimate from Josh Veer when he was at UC Davis. And the Forest Service estimates that about 70% are degraded, but it's really hard to know that exact percentage because all of the meadows haven't been assessed for their condition, and there are a lot of different ways to assess meadow condition as well. So there's some uncertainty here about how much meadow restoration is needed and what exactly does degraded mean. Okay, so that was all the work to assess where to do this work and how much forest thinning potential was there and how much meadow restoration was there needed. And then we shifted gears to really say, okay, well, we know a range of water benefits, whether it's water yield increase from forest thinning or the shift in timing of water with meadow restoration. So the idea, again, that the meadows store water in the winter and then release it in the summer. So we made some assumptions to do a benefit cost analysis about the value of water for hydropower, for irrigation, and for municipal and industrial. And we made the same assumptions across all of these different watersheds, recognizing that there's probably some, there's definitely probably some variation about, you know, which watersheds have more supply for irrigation or municipal and industrial, but for the scale of this, we just assumed all were the same. And for hydropower, we estimated that about 25% of any increase in water would be usable and would be valued at about 6 cents per kilowatt hour. For irrigation, we assumed that 70% of any additional water would be valuable for irrigation, and that would be worth $63 per acre foot in the winter and $100 per acre foot in the summer. And municipal and industrial, we assumed 20% of any increase would be valuable, and it will go to municipal and industrial and be valued at about $150 per acre foot. So this is important because we clipped, again, the watersheds to those big water supply reservoirs, which makes these estimates important when you consider them in conjunction with the actual infrastructure that exists to store the water. The study area, the watersheds have different amounts of hydropower. So in this table, we're just summarizing the existing capacity of hydropower in the watersheds. So the Feather River has the greatest amount of hydropower at 1,700 megawatts. And you can see some of the watersheds here do not actually have hydropower. So, for example, the Carson River in the Eastern Sierra doesn't have any hydropower. So that changes your value calculation. So to get at the cost of these activities, we knew that forest thinning had a range of costs from about $200 per acre to upwards of $1,700 per acre. depending on whether you're able to actually sell some of the material as, valuable timber, or you could offset the cost somehow with biomass or other valuable ways to use the forest thinning material. But we, in the end, decided to use just $1,000 per acre as an estimate of the cost of forest thinning. For meadow restoration, we estimated $10,000 per acre, and that was based on past plug and pond. We took a number of studies and then just took the midpoint of the range of the cost. We used a 5% discount rate, and the consultants ran a sensitivity analysis using a 3 and a 7% rate. The main point that I want to make is with this calculation of the benefit to cost ratio, or the total benefits divided by the total cost. When the value is greater or equal to 1, if it's 1, that means that the from water are completely offsetting the cost of doing the restoration work. When it's less than 1, it's the activity is paying for some portion of the water benefits are paying for some portion of the activity. So we found the range for meadow restoration was 0.02 to 0.03, which is really small. So in essence, the shift in water timing from winter to summer, the way that we've quantified it here and valued it, doesn't have a very convincing benefit to cost ratio. And what I mean by that is the water quantity shift doesn't really pay for the activity. So meadow restoration is quite expensive. The plug and pond, $1,000 per acre. And there are many different benefits besides just the shift in timing that come from meadow restoration. So this points me to think that maybe we can decrease the cost of meadow restoration in the future, or value some of the other benefits that come from meadow restoration to make this sort of more convincing as an activity, or more economically feasible. For forest restoration, it's different. The benefit you get from hydropower tends to change the benefit cost ratio to 0.08 to 1.3. So that range is showing you that for some of these watersheds, especially the ones that have a lot of hydropower facilities, the water yield increase from forest thinning would actually pay for the forest thinning work itself. So this is pretty interesting, and we got fairly excited about this result and are trying to take it now forward. These ranges are for 25% of the flow going to hydropower. We can also think, well, maybe they're actually able to use 100% of that increase in flow for hydropower, and that would shift the benefit cost range to 0.8 to 2. So actually, 2 is quite high. So there's some uncertainty here, but we get a sense that forest thinning could have real value, especially in terms of hydropower, by increasing the water yield and increasing your electricity production. Okay, I'm going to shift gears. So we've talked about the benefit to cost analysis that we did, and now I'd like to think about how these water benefits can relate to climate change. And so we all know that we're in a drought right now, and when you look at these two satellite images, you can see the comparison of snow coverage across the Sierra Nevada in 2013 in January compared to 2014. So drastically showing you the lack of snow that we have this year in essence. So how do we think about what's going to happen with climate change and how these management activities, forest fields reduction and meadow restoration, relate to projections of climate change and water supply in the future? So what I did was to use the VIC model, which the Bureau of Reclamation has downscaled on a very convenient website. So they basically took this model, it's a flow model, and downscaled it to a 12-kilometer square grid, which is still pretty big, but for the scale of these watersheds that we're talking about, it's actually appropriate. And I looked at an A2 climate scenario, which just basically means I looked at 16 models of climate change in the future, and those models are abbreviated on the x-axis here. And we can think about whether the annual amount of water, annual stream flow, is going to increase or decrease in the future. So here, the 0 line represents no change in the future. Negative values mean that the flow in the future is going to be lower, and positive means that you're actually going to have more water. So these lines are all the different watersheds. So the Feather River is the orange line here showing the greatest range of projected futures. And you can basically kind of eyeball and see that half of the models are showing a decrease in the future and half are showing an increase. So there's not a real clear picture about whether the flow in the future is going to be less or whether it's going to be more. And that actually is not too surprising given the Mediterranean climate that we have in the Sierra Nevada and the high variability in the flows. So what do we do with this? So what I did was I said, all right, let's just assume that the flow decreases in the future. So let's just look at the models, those 8 models for all the different watersheds that show a decrease in the future. So that's about 7 or 8 models in each watershed. And I evaluated whether forest thinning and the increase in water yield from forest thinning would actually meet those models showing a decrease. So for example, in the Feather River, if you did forest thinning on 30%, 33% on the watershed, would that water yield increase mitigate the projected decrease? I did the same for meadow restoration. So while the models are pretty uncertain on whether flow is going to increase or decrease on an annual basis, when you look at just the summer flows in the future, almost all of the models show that there's going to be a decrease. So this is showing you June and July flow in the future. So you can see most of the watersheds show a decrease or less than 0, a negative value for the future. So meadow restoration, again, when you restore meadows, you can shift the timing of the water. So can that shift in the water timing mitigate for these projections of decreased flow in the future? So less uncertainty in the summer flow decrease, still great uncertainty in the change in the annual flow. Okay, this is a bit of an overwhelming table, but I'm going to just pull out a few things. The forest restoration causes, a range of water yield increase. So for example, with the American River, it may, if you do the restoration work on all of the acres that are operable, you would probably get between 36,000 and 106,000 acre feet of water. And that would mitigate for one climate model showing decrease. So again, there are 8, and so it's only mitigating completely for one of those models that's showing a decrease. And this is using the high-end estimate, so 106,000 acre feet. In other watersheds like the Feather River, it actually mitigates for, the increase mitigates for 4 of the climate models, so about half showing a decrease. So actually forest restoration, if we assume that flows are going to decrease in the future, can mitigate for some of that decrease that is projected. The case with meadow restoration, when you look at the change in the summer timing of water, could mitigate for only one of the climate models showing a decrease in the Carson and West Carson. So by mitigate, I mean completely mitigate, like match the flow decrease. But even though it can't match completely, very many of the models, it can match a percentage of the flow decrease. So, it's not completely mitigating the flow decrease, but it mitigates about 15 to 25% in 2 of the watersheds. That's the West Carson and the Truckee River. So in those 2 watersheds in particular, meadow restoration could mitigate for some of that summer flow decrease that's projected. Okay, so just to summarize again, we were trying to do more of a planning study here, looking at increasing the pace and scale of forest fuels reduction or forest restoration and meadow restoration on public lands, U.S. Forest Service public lands. So I think there's a real value in scaling up and trying to estimate what the water benefits would be, because you're starting to make connections, hopefully then, between hydropower utilities or water suppliers that benefit from these restoration actions and payments, hopefully, for the actions themselves. So the forest restoration is expensive, and so is meadow restoration, and to actually get ahead of the curve and do a large amount of work that we're modeling here, these connections need to be made so that there's additional players brought to the table to think about the value to their bottom line, and if they value, then to help pay for these activities. So to summarize, we found that from forest thinning, the increase in water yield alone could match some of the costs. Again, that was when the benefit cost ratio was equal to 1 or above in some of those watersheds with a lot of hydropower capacity. With meadow restoration, the benefit cost ratio was not convincing, but when you look at the climate models and the fact that a lot of them show a decrease in that summer flow, you start to think, okay, well, meadow restoration can mitigate some of that decrease in certain watersheds. So again, I was talking about the West Carson and the Truckee. So this is work that's still underway, and we are outreaching with different water utility partners and working with the Forest Service to think about where to take this as a next step. We're pretty excited about the work and the potential to improve